Okay, when you use a computer, you are in competition with other users. With the student computing service, for example, there can be up to 31 other users, all trying to use the computer at the same time. And the sort of service you'll get from such a system is going to depend on its design. Well, it's no good just building a computer just to see how it works. It's far better to simulate it. Well, we've devoted the majority of the final block of units to simulation and to a language which we've called Simeon. And we've asked you in your practical to look at a computer terminal system. So now we're going to do an exercise in modeling this system and to produce a computer program.
So let's start by giving you the framework that we're going to use for constructing a simulation model of this real system, the student computing service. We first identify the features of the real system that we want to incorporate into our model. And we form a picture of how the real system works. We'll be drawing that here. And we'll call this a conceptual model. And it'll include the rules which govern the interaction of the main components of the system. Our next step is to produce a simulation model. And for a good conceptual model, it shouldn't be too difficult to form the corresponding model using Simeon blocks. And we'll be filling in this area here. So let's return to the real system and identify some of the features that we'll be building into our conceptual model.
Well, this computer terminal is connected to one of the SCS computers. So let's use it to see what features of a real system we can observe by actually interacting with the computer. I'd like you to have a look at this. The computer's asking me to log in, and I can do this quite simply by inputting my code. Well, there's my code, but it hasn't gone off to the computer yet. I can do this by pressing return. Now what's happening is that the computer is checking to see whether I'm a bona fide user of the computer. And so I am, because it says, go ahead. It's given me a message back in response to the message that I put in. So, suppose I get a program. Well, there's my message to tell the computer to get a program called ncroot. And what it's going to do is go away, search its files, find out whether that program exists. If it does, it'll let me play with it. So I press return, and this will set a task for the computer to do. Well, apparently it's found that program, so I could now run it. So I'll set the computer another task, that of running this program. And it's come back asking me for the option. Well, what's happened? I've put in a message, which is a task for the computer to do. The computer's gone away, done some computing, and eventually brought back some output for me. Well, all the tasks that we've seen on this terminal have been quite short ones. On this other terminal, which is connected to exactly the same computer as the other one, I've got a rather longer task for it to do. It's an LP program, and you know that LP programs take a long time. And I can get the computer to run this particular problem by simply typing in the option 1. So 1 return is the task, and the computer's trying now to solve the problem. Now here's an interesting thing. If I now try to type in another message, doesn't matter what it is, the computer's not letting me. It's effectively locking me out. Whilst it's doing the task of solving the LP problem, I cannot put another task in. Okay, so what has that shown? Well, it's shown that there's one and only one task associated with each terminal. But because there are several terminals connected to the computer, there are many tasks in the system, all competing with one another for use of the computer. Not only that, but each task will take a different amount of time. So it's these features which we can use to build a conceptual model of our computer.
So Pete's given us enough information from the real system to put together the main components to form a picture, our conceptual model. So let's form the simplest model that we can think of. In the conceptual model, there are several terminals. These communicate with the central computer through a communications device which we call a front-end processor. Its job is to channel tasks in and out of the computer. To simulate this conceptual model, we shall need to identify its main features. Suppose the guy at the first terminal is requesting an option from a package he's using. His message builds up in the store in the front end. The return character completes the message and is also the signal to switch off transmission. As far as this conceptual model is concerned, this message is just another task to be processed. It's identified with the terminal and sent to the computer. There's a store for any waiting tasks, and the processing is done in the central processing unit. The output is stored in a special store, and when the processing is over, any output is delivered to the correct terminal. The output message, in this case, is an option demand, and as soon as it's delivered, the terminal switches back to input mode. Here, there are just 3 terminals submitting tasks, sometimes data, sometimes functions. Any line of input creates a task. So let's see how this conceptual model deals with the demands of the 3 terminals. If the task from Terminal 1 is a very long one, then users at Terminals 2 and 3 are not going to get a very good service. Well, I'm not too worried about the service of those tasks. We can come back to improving our model later. But for now, we've got a picture to work on. We've identified the main features of the model: the CPU that processes the tasks, the queue store where the tasks wait if the CPU is busy, and the front end where the messages build up. So the next question is, how do we get the corresponding simulation model using the Simeon blocks?
Well, here's our conceptual model again with its 3 tasks. Now, to get our idea straight, let's look at it from the simulation point of view and just see what happens to one task as it goes through the system. Now, I'll remove those 2 tasks for the moment. And this task, the first thing it tries to do is seize the CPU. And we can show that with a Simeon block, seize. Well, if the CPU is busy, then the task will have to wait. If it is capable of seizing the CPU, then the task moves on and will hold the CPU for a certain period of time. And the Simeon block, appropriately, is called hold. The task remains in the CPU for a period of time and then moves on, releases the CPU so that other tasks can use it. So it'll release, picks up its output, and returns to the front end to output any messages. Well, it'll remain here for a period of time because it's got to output any messages. The user has to think about the messages. He has to think about what his response is going to be and whether he's going to input any messages. So this task is going to wait here for some time, and we can model that by another hold. If you like, it'll hold the front end for a period of time. So we've got a loop which goes seize, hold the CPU for a time, release it, return to the front end, and wait for the next task. Well, we just need a little more information. How long is this task going to use the front end for? How long is it going to remain for? Well, we can actually observe people at the terminal to see how long it takes them to respond to any input or output from this terminal. And we can come up with a distribution, which I'll call D1, of their reaction times. And we can sample from this distribution to find out a typical time to hold the front end. Now, at the CPU, we can do a similar thing. We can actually measure typical times that the tasks will hold the CPU for, and we can come up with another distribution. Maybe it might look something like this, a distribution D2 of CPU times, which we can sample from. Well, it's these four basic building blocks that we'll need to build up our Simeon simulation model.
For this conceptual model, we have these Simeon blocks: hold, seize, hold, release, and we've had to include a branch block to complete this loop. Now, Pete didn't explain how we get the three tasks into the model in the first place. Well, in Simeon, we do that by using a generate block, in fact, this generate block. This generates three tasks at the very beginning of the simulation. These then immediately flow onto this next block and subsequently round this loop. Now, also, I've used the name CPU. It's a facility in our model, and so we have to declare it as such using this facility statement. Another thing is these names D1 and D2. They're the names of distributions used for the sampling of times in these two hold blocks. Now, the 1 and 2 there link up with 1 and 2 in these dis statements, which specify the distributions. You can see that this is a histogram. It starts at 5, its interval width is 10, and there's 8 of them. The data statement tells us the heights of the histogram in each interval. Well, let's look at the model again. We've got a facility statement, generate block, and processing blocks, and data. And that's all I need to complete this model. So let's go to the computer and run it. Here's a complete listing of the model together with the line numbers. Now, if I enter the command run, then Simeon will immediately prompt me for the clock time when the simulation is to end. I'm going to use 6,000 units of time. Well, normally you would have to wait while Simeon carries out the simulation. But in fact, we did this earlier, and here's the results we got. You can see that the simulation finished at time 6009. And here's a report on the blocks. Simeon tells us how many tasks entered and left each block. So, for example, this block, number 20, which was the generate block, 3 tasks left there, while 437 entered block 30, a hold block, and so on. Also, Simeon tells us about each facility in our model. The CPU, you can see, was over 45% utilized in our model. So you might say that there's spare capacity on this computer. But as computer users, we're not always interested in the utilization of the computer. Often we're more interested in the response time, the time the computer takes to respond to our requests. And this information isn't given out automatically. We'll return to how we can get a hold of this later. But for now, let's see how we can get a better model, one which is nearer real life. You remember that with this system, the long tasks held up the short ones. In real life, the student computing service computer, for example, allocates each task a fixed amount of time. The question is, how do we incorporate that into our conceptual model? The problem was that task 1 kept hogging the central processor. The idea of time slicing is to allocate each task a set amount of time. When this time is up, the task has to make way for the next. Task 3 seizes the processor and could well finish within its allocation. Task 2 gets its time slice. Then, task 1 can carry on from where it left off before. In this way, long jobs don't hold up the short ones very much. Follow what happens to tasks submitted by Terminal 3. Now look at it from Terminal 2's point of view. So with this new loop, all of the users are getting a fair share, and we've got a much better model.
Well, here's our conceptual model again, with its extra loop. But there's a problem. When the task seizes the CPU, the simulation won't know how long to hold the CPU for. Does it hold it for a complete time slice, or for a period less than a time slice? Well, we can answer this problem if we introduce the idea of an attribute. To see how it goes, let me just remove these blocks, because after all, they're not going to change. And I'll leave the distribution D1 where it is for the moment, because I want to use that. What the simulation has to do is determine the time for the hold before actually embarking upon the hold. And of course, it can do that because we've already got the distribution D2. And we can sample from D2 and store the value in an attribute, at1. And you can think of this as the hold time being carried around the model by the task. Now this means that as the task moves on and attempts to seize the CPU, the simulation can ask the following question. And we can decide that if the attribute is greater than the time slice, which for the moment we've chosen arbitrarily to be 12, then the task can hold the CPU for a complete time slice before moving on. If, of course, the attribute is less than 12, then the task will move down the old loop back to the front end. Well, in this situation, when there is more than 12 units of CPU time required, the task will remain here for 12 units and move on round the model. Now, at this point, we can, in fact, subtract from the attribute the time slice of 12. And this means that the value in the attribute is now the time remaining that the task needs to use the CPU for. So we can come back round into the store and use the CPU again. But of course, we don't want to sample again at this point. We already know the time that's required. So this sampling process must be done before we get into this loop. And I can do that if I move the sampling process before the loop. So for our new model, we'll need 3 new blocks associated with the attribute and, of course, an extra loop.
So for this time-sharing model, we have these Simeon blocks, and this is the complete model. Here you can see the 2 loops. Here you can see the early setting of the processing time. We're sampling from distribution 2 and storing the value in attribute 1 of each task which passes through this block. Here's the test. And here's the new loop. We're processing for the time slice, calculating the remaining time before branching back to await the CPU again. And here's the loop for processing those tasks that require less than the full time slice, or whose remaining time is less than the full time slice. Well, earlier we entered this model into the computer and we obtained the same type of results as we obtained before. Here's the block count. And this is followed by information on the facility. Now, to get more than this, we must use special blocks called on and off. And Simeon records the time tasks spend between these two blocks. Now, if we're interested in getting the response time of tasks, then we must position these on-off blocks to record that response time. Well, we need to first record the time when the return button is pressed, and that corresponds to this point in our model, and so we'll put an on block there. Now, some of those tasks, the short ones, will come straight through here before looping back with their output, while others may go around this outer loop and then subsequently flow through this part of the model. All tasks come through here before they branch back with their output. And so if we put an off block there, we'll record the time just before they return with their output. So on and off will measure the response time. Now, when we entered those new blocks into our computer model, we obtained these results. We obtain a histogram. And the histogram tells us the number of tasks that spent certain times in the system. For example, here 109 tasks spent between 0 and 4 units of time, where 107 spent between 4 and 8, and so on. The average time of all of the tasks is 8.5 time units. Well, as part of your fourth practical unit, we've asked you to investigate these systems further. What happens when you change certain parameters? Suppose, for instance, you have two classes of tasks, short ones requiring only small amounts of CPU time, and the larger ones. What happens if you vary the time slice, or increase the number of terminals on the system? It's through simulation that we can investigate these systems without altering the real system. Well, this is your last practical unit. I hope you'll enjoy it. And as you finish the course, we hope that M351 has put you on the right road to good numerical computation.
Well, that was the final program for the third level course on numerical computation, but you may like to know that it'll be presented again next year as one of the courses in our associate student program. If you'd like to apply, why not send off for a free copy of our 1986 Continuing Education Guide by writing on a postcard, please, to this address. The Associate Student Central Office, The Open University, P.O. Box 76, Milton Keynes, MK7, 6AM. Now, Brian or Rosemary. Candidates for posts in education often look back on staff selection panels as hit-and-miss affairs. Selectors usually challenge this view. Today's program for the third-level course, Management in Post-Compulsory Education, presents a simulation of the staff selection process at a college of further education.
What I like to do, we've got all the sort of preparatory work out of the way. What I like to do is
Candidates for posts in education often look back on staff selection panels as hit-and-miss affairs. Selectors will usually challenge this view. This program looks at the way the assessment of candidates is related to their interview performance.
so you carry on the question. John there. And then from you to your head of section, Gordon here.
The interview panel for a Lecturer 2 post in Liberal Studies at Linton College is chaired by the Principal, Mr. Lewis.
And then, if I may, I'd like Ian to hand over to you.
Ian Stewart is overall head of Liberal Studies at the college.
I think there's differences between the two of them, though. And I think we have to decide at some stage before we interview them whether we're going to lay emphasis on those differences.
Then from you to your head of section, Gordon here.
Gordon McAlpine is Ian's deputy and head of the Liberal Studies section.
The work in itself is in a developmental stage, and things are changing all the time, so we're looking for somebody that's got that vision.
And then, if I may, to you, John, as the representative.
John Ross is a course tutor for science students, an academic board representative.
Well, certainly I've got a question which I'd like to ask to both of them. But I wondered if it's worthwhile just looking through the references and the application forms in detail.
And Mr. Morris?
Christopher Morris is Mr. Lewis's deputy.
My attitude is that you're always looking for a lot more than you can get.
Brian Harrison is the first of two applicants to the job of Lecturer 2. He's 34, married, and currently Lecturer 1 in charge of sociology at Eton College of FE, a job he's been doing for the last 9 years. We're going to show you 5 minutes of a 30-minute interview with him, which will tell you as much about the panel as about the candidate.
I think the first relevant point, if I may, is that I see you're 34, married, and family, right?
Oh yes, I have 2 small children.
2 children, yes, indeed. Your education background, well, Hayford High School, Liverpool, where O-levels, A-levels, and so on, 4 A-level passes, I see. Then, straight on, was it to the university? No, on to the University of Waterford.
No, I took a year out at that point, and I was working as a lorry driver for a short while.
I'm confused by one thing, Mr. Lewis, and that is he said 67 and 70 he started at the university. What did you do for the other 2 years?
So that was the time I spent out working before I went off to university. Between leaving school and going to university, I spent some time working.
Yes, but there's 3 years there. Did you... 67, unless you got the dates wrong, 67 to 70.
Such a long time ago.
Yeah.
I spent about 18 months working for AEI Cables.
Yeah.
And I spent some time in America at that time.
Ah, you went to America too?
Yes, yeah.
What did you do in America?
I was just travelling around and did some working over there. It was a little easier to find work in those days than it is today.
Thank you. I thought it was more than a year.
Right, thank you, Mr. Morris.
Let's move towards the wider spectrum of liberal studies in general. It's been known by quite a few things through past years, general studies, communication studies, now currently a phrase, social and life skills. Which approach do you feel comfortable with?
Personally, I feel most comfortable with communication skills, trying to get young people to discover the kinds of things which influence their everyday life, and trying to get them to come to terms with that and possibly to manipulate those situations to their own advantage. The worst thing you can possibly do is to try and take into a liberal studies classroom sort of preconceived notions of sort of art and culture and what students think should be, what they should be learning, sort of giving them a crash course in the history of English literature or something. But that kind of approach quite clearly doesn't work, and you need to sort of be working from students' interests, I think, in the first instance.
It's a group you've never met before. See, it's a third-year craft group, and you haven't seen them before either, first or second year craft students. What would you be first main opening